right, so let us start again. I'm Rupinder from gotouniversity.com, and we have launched a free CBSE portal tailored with uh, the all the mock test papers, past papers, and everything, where you can have free access to the study material. All right. So we have designed this portal for specifically for CBSE board exams, where we have launched uh, exclusive access to 10 mock test paper per subject, which are crafted in line with CBSE board exams. You can have also convenient access to past 5-year papers for your comprehensive preparation. You can also do self-evaluation for mock test as well as past papers, with the ability to share answers for independent assessment by another teacher. Also, you can have free access with high quality study materials, which are organized by topics and subtopics for each subject. You can also have access to 10,000 practice questions for deepen your understanding, which are also designed by topic as and subtopics for each subject, right? So many of our students have achieved merit position in CBSE board exams. So take the advantage of this opportunity to elevate your learning experience and excel in your academic journey, right? So as you can see here on the screen, we were doing in our previous class the chapter Electrochemistry, where we have studied covered some important topics as Nernst equation. We have done electrochemical cells. Okay, we have done Daniell cell in brief. We have done their constructions and the working of the cell. All right, we deeply understood the working of galvanic cell and how to apply Nernst equation, what is the Nernst equation, and the equilibrium constant, which that relates to Nernst equation. Okay, we have studied about Gibbs free energy also. Okay, can you tell me what was the formula for Gibbs free energy? Reversible Gibbs free energy, it was minus NFE, right? Right, and from this we can check whether the reaction is spontaneous or not. For Gibbs free energy, if it is having positive value and negative electrode potential, then the reaction is known as spontaneous, and vice versa. All right, so let us move to our today's topic, which is conductance of electrolytic solutions. Okay. So, as I say, before moving to electrolysis in conductance solution, we need to get familiar with some definitions. So, we were discussing about the friction, that as we know that to walk on floor, friction is necessary, right? So, in a similar way, when a current is passing through a setup, it also face some kind of friction, and that friction is termed as electrical resistance. All right, it is similar force like a friction, where when electricity is being conducted through a system, it experiences a certain friction, right, which is also known as electrical resistance. It is uh, denoted by capital R. Okay, it can be represented by capital R, and it is what, if you can read the definition here, it is a hindrance to the flow of electric current. Okay, and the SI unit of measurement of electrical resistance is ohm. Okay, so its unit is represented by Greek symbol, which is called omega. Okay, this symbol is termed as ohm. Okay, for this electrical resistance, we have also studied this electrical resistance in Wheatstone bridge, which you have studied in physics class also. Okay, so mathematically how we calculate the electrical resistance, it is resistance is directly proportional to L by A, where L is what? It is the length of wire, or say metallic wire, and A is the area of cross section. Okay, so 1 ohm, it is equals to kilogram meter square over upon Simon cube to per square. Alright, so this is the unit for calculating electrical resistance. Okay, if we look at this relation, R is directly proportional to L by A, where R is the resistance, L is the length of conductor or say metallic wire, A is the area of cross section. Now if we remove this proportionality constant, we can use here this directly proportional sign. We use here one proportionality constant, which is known as rho, and it is termed as specific. It can be read as rho. Okay, the symbol is like P, right? It is termed as resistivity constant, or say specific resistance. Okay, this resistivity, the value of this resistivity, or the unit for measuring the resistivity, is ohm meter. Okay, if we revise this concept again, what is electrical resistance? It is the hindrance, or say it is the stoppage that is observed by the flow of current, okay, in the conductivity cell. Its SI unit of measurement is ohm, which is a Greek symbol. In the Wheatstone bridge, we have studied in physics that there are 4 resistance, in which one resistance is unknown. Okay, we will discuss this in our upcoming slide. Mathematically, we calculate resistance using this expression, where resistance we take, it is directly proportional to L by A, where L is the length of metallic wire, okay, and A is the area of cross section. When we use this, or we can write this as R is equals to rho L by A, where this P symbol, or say this rho, is specific resistance or resistivity constant. It is measured in ohm meter. All right. The next term we need to familiar with are conductance and conductivity, which are very important. Conductance, it is the opposite of resistance. Conductance is what? It is the opposite of resistance. Okay, that is that conductance is what? That allows the current to flow. Okay, it is also written here that conductance is what? It is the reverse of resistance, which allows the current to flow smoothly. The SI unit for conductance is S, and conductance is represented by the capital G. Its SI unit is Siemens, which is equivalent to mho. As you have just seen that for resistance we use the unit ohm, and conductance, as it is the opposite, so we have also reversed its unit as mho. Okay, that is ohm, that is mho inverse. All right, now what is conductivity? For conductance we can also try the relation as we have done for resistivity, that conductance, that is Z, it is the reverse of resistance, or say G is equal to 1 by R, okay, where resistance, what is the resistance? It was L by A, right? So we can write here G is equals to A over L by rho, alright, which is equals to kappa, which is a conductivity constant, okay, A by L, okay. So this is the relation for conductance, okay, where K is what? It is termed as kappa, and that is also known as conductivity constant, okay, as written here, okay. So conductivity is what? It is represented by K. It is called specific conductance, and it is inverse of resistivity, that is this. Okay. So how these relations, these two are related to each other? As we have discussed that conductance was what? It is the reverse of resistance, right? And resistance was what? Rho over La, right? So that means conductance is what? 1 over rho La, right? Which will become A over rho L, right? And conductivity is what? Here it is the inverse of resistivity, right? It is the inverse of resistivity. So that is why inverse of resistivity. What is resistivity? It is, that is 1 by P. Okay, that is 1 by P. So that is why G, it can be termed as kappa A over L, where this is what? This is 1 over rho, that is kappa. Understood? It is also known as conductivity constant. Alright, moving on to next for some other definitions. So based on conductance, the magnitude of conductance, it depends on nature of substance, right? The magnitude of conductance, it depends on nature of substance. It depends on what? Nature of substance, that whatever the conductivity is being produced, that how much a substance can conduct electricity, it is based on what kind of substance we are using, or what is the nature of substance. Okay, so based on that, based on the magnitude of their conductance, we have divided, or we have categorized these substances into 4 types. Okay, that is conductors in which the resistance will be low, that they will be facing low resistance and showing high conductance. So the substance that show high conductance and low resistance, they are termed as conductors. Okay, so this is a very basic thing that you have studied in previous classes. The conductors are what? Through which current can easily pass through. Okay, that means the substances which shows low resistance to current and shows high conductance. Okay, examples for conductors are metals, okay, metals and their alloys, metals and their alloys. Other than that, graphite, Carbon black and organic polymers are also examples of conductors. By organic polymers, we mean, for example, polyaniline, okay, or say polypropylene, okay. So these are some example of conductors, right? Other one is insulators, okay. Other category is insulator. Insulators, it is the opposite of conductors. That means it shows high resistance to the flow of current, okay, and they show low or say zero conductance, okay. Examples of insulators are glass and ceramic. What are semiconductors? Semiconductors, they are neither conductor nor insulators, okay. They are somewhere in between, okay. They ranges somewhere in between conductors and insulator. For example, they can conduct electricity for some time and then they turn as insulator. Then again they fluctuate between conductor and being an insulator. Example for semiconductors, they are silicon, doped silicon, okay, doped means silicon with impurity, and germanium, arsenide, germanium arsenide, etc. Okay, so semiconductors are what? Which are neither conductor nor insulator. Then the last category based on the conductivity of different substances is superconductors. Okay, superconductors are what? They offer zero resistivity. That means the current will flow in high amount. That means they will show infinite conductivity. However, for metals and their alloys, for, to act like superconductor, they need very low temperature, generally for 0 to 15 Kelvin. Okay. Now, 0 to 15 Kelvin temperature, it is very low temperature, right? So around that temperature, around at low temperature, resistivity, it drops. Okay, resistivity, it decreases. But as resistivity decreases, conductance, it increase, right? So that is why they start acting as superconductors, okay. But to but this temperature is hard to achieve, all right. this is this temperature, say this temperature is not economically feasible, okay. This temperature is not economically feasible, so that is why to have superconductors available easily, they're not easily available, okay. So unless there is a need of superconductors, we cannot use superconductor easily, okay. They are not readily available, okay. Why? Because attaining this low temperature is economically not feasible, and such temperature, it is hard to achieve for metals, okay. So after reading this, let us move on to our next topic, that is the electrical conductance, the factors on which electrical conductance depends. So what are the factors on which electrical conductance of electrolyte solution depends? It depends on four factors, that is the nature and concentration, which is very important, nature and concentration of an electrolyte, okay. Now let us discuss them one by one. the factors on which ionic conductivity or say electrolytic conductivity depends are their nature, okay, and concentration. The nature of ions produced, in this we will discuss the solvation of ions, okay, and viscosity and nature of solvent, and the temperature that is inversely proportional to ionic conductivity. So how the ionic conductivity depends on the nature and concentration of ions. Okay. Now if we are taking an electrolyte, which is, there are two types of electrolyte, weak and strong electrolyte, that you must have studied in grade 11. Okay, weak and strong electrolyte. Now this weak electrolyte, its conductivity, it shows low conductivity. Okay, or say their molar conductivity is low. All right, so that is why it depends on the nature of electrolyte. If we are using strong electrolyte, okay, then the conductivity of an ion will be high. If we are using low or say weak electrolyte, the conductivity, overall conductivity of a solution will be low. Okay, for it also depend on the size of ions. Okay, the size of ions produced. If the size of an ion is large, okay, if the size of ion is large, then the speed of conductivity will be low. Okay, it lowers speed of conductivity. How? As the size of ion is large, it will be hard for them to move on to other direction. Okay, so that is why the conductivity rate, it decreases. All right, what is the next? It also depends on the nature of solvent. Okay, nature of solvent and viscosity. What is viscosity? It is the thickness of solution. Viscosity is what? Thickness of solution. Okay, now if the solution is thick, okay, or say the solvent, it is having high viscosity, then also it will lower the speed of conductivity. Okay, it will lower the speed of conductivity. All right, next, if we talk about the concentration of electrolyte, then with the increase in construction of electrolyte, the conductivity decreases. Okay, right. Next, if we talk about this last factor about the temperature, that is inversely proportional to the ionic conductivity. Now, the conductance or say conductivity or say ionic conductivity, it increases with increase in temperature. Okay. How? See, with the passage of current through electrolyte on changing its composition through electrochemical reactions. Okay, if the current is passing through electrolytic solution with high temperature, its conductance will increase. Okay, so I hope these four factors are clear to you, that how the electrical conductance, it depends on what factors. Okay, so if you can read here again, the ionic conductance or say electrical conductance of an electrolyte solution, conducts electricity due to presence of ions in solution, right? The ionic conductivity depends on nature, that what is the nature of solution or what is the nature of electrolyte we are using. Is it weak or strong? For weak, conductivity will be less. For strong electrolytes, conductivity will be high. Okay. Nature of ions produced in the solution, where we will discuss the solvation of ions. The solvation of ions are what? It is the solute particles combining two solvent molecules. Two solvent molecules. Okay. So this also decreases the conductivity. All right. When the solute particles they started combining with the solvent molecules rather than moving to the other direction to show electrolytic conductance, it also lowers the rate of conductance. Okay. Then we have discussed how ionic conductivity depends on the third factor, that is viscosity and the nature of solvent. If the nature of solvent is viscous or solution we are using is thick, then it will also decrease the rate of conductivity. Okay. Then we discuss the temperature, that is inversely proportional to the ionic conductivity. All right. Now let us move on to how we measure the conductivity of ionic solution, or how we calculate the ionic conductivity. Okay. To understand this, first we need to discuss what is a cell constant. Okay. Now in Wheatstone bridge, where we have two problems, if you can read this, which helps in the accurate measurement of unknown resistance of a non-ionic substance. These ionic solution resistance can be measured by Wheatstone bridge. So as I've discussed in Wheatstone bridge, we were doing what? We were doing the calculation to measure an unknown resistance, okay, which were forming due to non-ionic substances. So here I have mentioned two problems which we were facing while discussing Wheatstone bridge, or while measuring resistance in Wheatstone bridge. The application of direct current, it changes the composition of ionic solution as I have just discussed. So alternate current has been introduced or has been used as a source of power in place of direct current. Okay. This alternate current has been introduced for use in conductivity cell. Okay. For the other problem, the ionic solution, that it cannot be connected to a Wheatstone bridge like a solid substance or using a metallic wire. So to solve that in conductivity cell, we have designed such an ionic solution where we took resistance of that ionic solution is equals to unity. Okay. And where we have used this formula for resistance, that is rho L by A. All right. In that L by A, we kept them as same value, or say unity, where we find the G star, or say cell constant, right? For this relation, we used what? L and A is equals to same. Okay. Then we find the relation, this relation, okay, which is termed as R is equals to kappa, or say cell constant. All right. Now let us study some principle or some methods to measure the resistance or conductivity of any solution. All right. So there is as we have discussed that there is conductivity, which is represented by G, okay, and then there is molar conductivity, which is represented by lambda m, okay. Now what is the relation between this conductivity and molar conductivity? Conductivity we have already discussed, right? And what is molar conductivity? Molar conductivity means 1 mole of solute, it means 1 mole of solute, okay, present in solution, okay. Or molar conductivity of a solution means that the solution is of molar, 1 molar concentration. Say if we are preparing dilute solution, the molar conductance for 1 mole solution will be, yes, we have discussed in our previous sessions that it will be 10 ml of, or say 1 ml of solution, and rest will be the solvent, right? So the molar conductivity means that 1 mole of solute present in solution or solvent, okay. It is what? It is the conductance of volume of solution containing 1 mole of solution. If we write a proper definition for molar conductivity here, that it is conductance, okay, of volume of solution containing 1 mole of electrolyte, all right, 1 mole of electrolyte between electrode of unit length in area, okay. That means that delta m, it is equals to kappa A by L, that is equals to K, where we are taking A and L is equals to 1, okay. Using this, we can say that lambda m is equals to K, all right. Okay, now if we take in this relation lambda m is equals to kappa A by L, okay. If we take here L is equals to 1 and A is equals to volume of 1 mole of electrolyte, 1 mole of electrolyte, will become, this will become delta m, sorry, lambda m, that is molar conductivity, is equals to kappa into V, all right. Also, we know that kappa is equals to cell constant by resistance, right? So therefore, by substituting this kappa value in here, we will find that lambda m, or say molar conductivity, it will become equal to kappa over C. All right, this is what molar conductivity, where K is conductivity constant and C is concentration. So here we can say that molar conductivity is what? It is having inverse relation to concentration. If the concentration of a solution increases, the molar conductivity decreases. As I have discussed, what is molar conductivity? It means 1 mole of solute present in solution. Now, if we increases this concentration of solute, okay, if we are increasing this concentration of solute in the solution obviously concentration will increase, and as molar conductivity is having inverse relation to concentration, then the molar conductivity of a solution will decrease with the increase in concentration, right? So let us read here. A cell constant can be used. What is cell constant? G star, that is used to measure what? The resistance or say conductivity of a solution. This is a Wheatstone bridge. Here we are having galvanometer where all the resistance they are attached to galvanometer. We are having a battery here. When the current start flowing from these resistance, okay, where we face two issues, that we cannot connect the solution using metallic wires. All right, that is why we discovered or we introduced conductivity cell. Okay, for that direct current, it was passing through these resistance causing chemical composition here, chemical reaction compositions. For that we used alternate current in conductivity cell, right? So to measure the cell constant, okay, to measure the conductivity of a solution or say resistance, we introduce cell constant that is used to measure the resistance or conductivity of the solution. Okay, here in Wheatstone bridge you can see two resistance, these R3 and R4 which are variable. Okay, R1 is the conductivity, R1 is conductivity cell, this R2 was unknown resistance. Okay, and these two were variable resistances. All right, for unknown resistance we use this formula to calculate unknown resistance R1 into R2, that the conductivity cell resistance and the variable resistance by the other variable resistance, right? Then we have discussed what is molar conductivity, that is the ease or speed with which ions move under the action of a potential gradient. What is molar conductivity? Which it means that 1 mole of solute present in a solution, right? How we calculate this? I have discussed with you its relation with conductance, right? That lambda m, it is represented by lambda m, molar conductivity, okay, and it is equals to this relation kappa into A by L, okay. If we use A is equals to volume of solution, that is V, and L is equals to 1, then lambda m will become equals to this, right? And also as we know that kappa value is what? G star by R, then lambda m, it will become kappa by C, okay, as discussed here. Now what is the unit, SI unit of molar conductivity? It is Simon meter square per mole inverse. All right, our next subtopic, that is variation of conductivity and molar conductivity with concentration. What that means is that how the conductivity, okay, and molar conductivity, it varies. There is one more thing related to molar conductivity, right? When concentration it becomes 0, molar conductivity was what? It means the 1 mole of solute in solution, right? 1 mole of solute in solution, right? Now at times when the concentration of solute it becomes 0, then the molar conductivity it also becomes 0, and that molar conductivity, that is lambda m0, it is termed as limiting molar conductivity, right? So here are given the proper definitions for molar conductivity and limiting molar conductivity. This is also used in numericals, okay, limiting molar conductivity, right? So how the molar conductivity and conductivity varies with the concentration, I think it is clear to you already. That concentration is what? First, it is the concentration of electrolyte it changes both the conductivity and molar conductivity, right? As we have discussed that there are two types of electrolytes, strong and weak electrolytes, okay? And the and the concentration of solution for both strong and weak electrolytes is inversely proportional to conductivity, right? If we are using weak electrolyte, the conductivity will be low. For strong, the conductivity will be high, okay? For molar conductivity, as it is the inverse relation, so the conductivity will vary in molar conduction, right? But this molar conductivity is also known as conductance of electrolytic solution maintained between electrodes of conductivity cell, okay, with a unit distance and cross-sectional distance. As we have discussed, unit distance is what? This is L and cross-sectional area is A, right? Where we took this unit distance as volume, right? Volume of solution, right? From where our lambda m, it will become equal to this kappa v, right? That we have just discussed. So these are here the theoretical definitions for we have just discussed now, right? And limiting molar conductivity is what? It is represented as lambda naught m. It means that concentration of solute in the solution, it has become zero, and that is why called limiting molar conductivity. All right. Now, as we have discussed, there are two types of electrolytes, strong and weak electrolytes. Sometimes a question come in exam where examiner can ask difference between strong and weak electrolytes. All right. So let us discuss them. Strong electrolytes are what? They are having molar concentration. Their molar concentration increase slowly with the dilution, as I have discussed. For weak electrolytes, conductivity decrease. Okay. For strong electrolyte, as it is inverse relation between conductivity and molar conductivity. For weak electrolytes, molar concentration, it will increase. For strong, it will decrease. But if we consider conductivity for weak electrolytes, it decreases. If we consider molar conductivity for weak electrolytes, it increases. Okay, why? Because molar conductivity, it is having inverse relation with conductivity, right? For strong electrolyte, there is a straight line graph that is plotting between molar conductivity and concentration. Okay, and here no straight line obtained. For molar concentration of strong electrolyte, that is obtained from the intercept of straight line. Okay. For limiting molar conductivity. Okay, here limiting molar conductivity of weak electrolyte, it is obtained from Corraj's law. That is law for independent migration of ions that we will discuss shortly. Okay. Example for strong electrolytes are NaCl, KCl, magnesium sulfate. For weak electrolytes, it is acetic acid, CH3COOH. Okay. Now, what is Corraj's law? That we have discussed in weak electrolytes, that it is independent migration of ions. Now, let us read here. According to Corraj's law, the combined conductances of anions and cations, okay, they are determined by the equivalent conductivity of an electrolyte at infinite solution. Now, what that means? This means that the conductivity of a salt solution, say NaCl, or we can take an example here of NaBr, that is equal to the sum of the conductances. Now, what are, if we see here NaCl, what are the cations and ion here? Here NaCl, this is what? Cation, and this is an anion. if we have to calculate their conductivity, that will be the sum of these both cation and anion, right? So the conductance of salt solution, it is equal to the sum of the conductances of these ions, anions and cations, right? For limiting molar conductivity of NaCl, what was limiting molar conductivity? The conductivity at concentration 0, right? For this, we can represent it as like this. Okay, that is what? The sum of the conductances separately for cation and anion. That every cation and anion, they will be having their specific conductivity, and molar conductivity, they can be presented according to Kohlrausch's law as they migrate independently. So for molar conductivity according to Kohlrausch's law, we can calculate their conductance separately, okay, by adding them. All right. Now, where we apply this Kohlrausch's law? Why we use Kohlrausch's law? What are its application? First, it helps us to calculate, as we discussed, the molar conductance of weak electrolytes. Okay, by combining their the molar conductivity of cations and anions separately, right? And the degree of dissociation of weak electrolyte, it can also be measured with Kohlrausch's law. If I write here an example that we just discussed for this NaCl anion, okay, the molar conductivity, it was represented. Now this ion, it dissociates into what? Into cation, okay, and anion, right? So at what extent these cation and anion, they dissociate, we can calculate their degree of dissociation with the molar conductivity dividing by its limiting molar conductivity, right? It is a degree of dissociation, it is represented by alpha, that is the molar conductivity of that ion divided by their limiting molar conductivities, okay, that their molar conductivities at 0 concentration, right? It also helps us to calculate the solubility of sparingly soluble salts, sparingly soluble, that are less soluble in solvents, right? So solubility we have discussed, it is equals to kappa into 1000 if we are using the, if we are taking the amount in centimeters, right? This is very important. Okay.